Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will discuss another topic. Let me write the topic. Our today's topic is using the complex exponential. Let me underline this. Using the complex exponential. Remember, in the last lecture, we discussed Euler's relation and its geometrical interpretation. Euler's relation is Ej theta is equal to cos theta plus j sine theta. Ej theta is equal to cos theta plus j sine theta. So this is our Euler's relation. Now we want to understand why is it important contribution to the analysis of vibrations. Why Euler's relation is important contribution to the analysis of vibrations. We will see it makes our work easier, and the prime reason for that is all of you know that if we differentiate exponential function, we get the function back. D by dx of e raised power x is e raised power x, and obviously if we integrate this function, we get the function back. This property of the exponential function, that if we differentiate it, we get the function back, and if we integrate it, we get the function back, is the prime reason for Euler's equation to become important contribution in the analysis of vibrations, because this Euler's relation converts this combination of cos and sine into an exponential function. So that makes our life easier. Let us try to understand it. We take an example. We have already discussed that there is a relationship between simple harmonic motion and uniform circular motion. So let us set up a uniform circular motion in xy plane. Let this be my xy plane. And what I do, I set up a circular motion. Let this point P be moving along this circle in this fashion in uniform circular motion, then let O be the origin, and origin becomes the center of this circle. So now this, as this particle moves, this OP vector rotates, and let A be the radius of the circle. So this has length A, and we know when there is uniform circular motion in this way, then there are two corresponding simple harmonic motions. So P has one projection, we call that P prime on x-axis, and another projection, we call that Q on y-axis. So P executes uniform circular motion. We name it figure 1. P prime, which is the projection of P on x-axis, executes SHM, simple harmonic motion. And Q, which is another projection of this point P on y-axis, also executes simple harmonic motion, right? Let the angle formed by OP vector at time t be omega t plus alpha. T is time, omega is angular velocity, angular velocity of P, which are we assuming to be constant because motion is uniform circular motion. T is time, alpha is some constant, right? And let this OP prime distance be x and OQ distance be y. This is y, this is x. And you know, as P moves along the circle, P prime also moves, Q also moves. So x and y change with time, right? From this figure, it is evident that this x, which is time dependent, is simply a cos omega t plus alpha. Let me name it first. And y, which gives me position of Q, is a sine omega t plus alpha. This is my second, right? So x is a cos omega t plus alpha because it is the projection of OP on x-axis, and y is a sine omega t plus alpha because it is the projection of OP, that is OQ, on y-axis. So as P moves, P prime moves, Q moves, and hence x and t change with time. You can see the equations 1 and 2, which give us positions of P prime and Q, are the equations for simple harmonic motion, A being the amplitude of motion for these oscillations, omega the angular frequency, alpha the phase constant. And also you know that these two oscillations correspond to one uniform circular motion. These two SHMs have same amplitude, and that is equal to radius of the circle, which is a in this case. They have same time period because frequency is same, but they are out of phase by 90 degree because equation 1 involves cos, equation 2 involves sine, right? Now, if we have to analyze simple harmonic motion, we think of it, or we make calculations related to the simple harmonic motion in terms of the motion of P, in terms of the uniform circular motion. Actually, we have to discuss the motion of P prime. For example, the simple harmonic motion taking place on the x-axis, we set up mathematically a uniform circular motion, but in doing so, we get one more oscillation along y-axis. So what we do when we make use of this complex exponential, use of complex numbers, we do the calculations, and at the end, this y motion becomes the imaginary part of our results, and we discard it, and we take the real part, which is x, as our final result. So let us see what we do. So if I find dx by dt, I have to differentiate. That will give me the velocity of P prime. What is dx by dt? Dx by dt is simply minus a omega sine omega t plus alpha. It is different. We have to differentiate equation 1 with time. Cos, derivative of cos is sine, and we get, sorry, derivative of cos is minus sine, and we get this omega outside as a multiplier. So dx by dt is minus a omega sine omega t plus alpha. So this gives us then the velocity along x-axis, or velocity of P prime. Now, if we want to find the second order derivative of x with time, that is the acceleration time function, that is the acceleration of the simple harmonic motion taking place on x-axis. It is simply the derivative of this thing, which is minus a omega square cos omega t plus alpha, minus a omega square cos omega t plus alpha. When we differentiate dx by dt with time, differentiation of sine is cos, and we get one more omega outside, so it becomes minus a omega square. Now we want to find this is velocity and acceleration for P prime. We want to find the velocity and acceleration for Q. For that, we have to differentiate y with time once and twice. So let us find dy by dt. So dy by dt is a omega cos omega t plus alpha. You can see when you differentiate this, derivative of sine is cos, and you get one more omega outside. So you get a omega cos omega t plus alpha. Then the acceleration along y direction is second order derivative of y with time, which is minus a omega square sine omega t plus alpha, minus a omega square sine omega t plus alpha, right? So let me write, I will use this color. This is position of P prime. This gives me position of Q. This gives me velocity of P prime. This gives me acceleration of P prime. Similarly, this gives me velocity of Q, and this gives me acceleration of Q, right? You can see we have 6 equations, 3 for motion along x-axis and 3 for motion along y-axis, 3 pertaining to one simple harmonic motion and other 3 pertaining to other simple harmonic motion. On the other hand, if we work with, let me use another color. On the other hand, if we work with the combination x plus jy with x and y as given by equations 1 and 2. 1 is this, 2 is this. See what we get. So we combine 1 and 2 in the form of a complex number x plus gy, right? So what we get, let me use another page. We have what we have z equal, z denotes the complex displacement or complex position. It becomes a cos omega t plus alpha plus j a sine omega t plus alpha, right? You can see this thing is x and this thing is y from first and second. X is a cos omega t plus alpha, y is a sine omega t plus alpha, right? You can simplify it. I can write it a, can take a out. A is common to both terms. It will become cos omega t plus alpha plus j sine omega t plus alpha. Now I can use the Euler's equation. Cos omega t plus alpha plus j sine omega t plus alpha becomes e raised power j. So I guess third is a e raised power j omega t plus alpha, right? Let me encircle it. What is this? A e raised power j omega t plus alpha. It is the complex displacement. It contains both displacements x and y mathematically, right? Now, if we find Let me name this. This is equation 3. Let me find its derivative with time that will give me the complex velocity. This is, let me write it, complex position. Now differentiating this with time, let me use another page. Now dz by dt is simple to differentiate, is a j omega e raised power j omega t plus alpha, or I can write it j omega z. This is my complex velocity. We check it. dz by dt is a j omega e raised power j omega t plus alpha. This is j omega z, because a e raised power j omega t plus alpha is just z, as you can see. It's easy. We are differentiating it with respect to time. A is constant, that will be out. So when you differentiate e raised power j omega t plus alpha, this function comes back like this. But you have to then multiply the differentiation of j omega t with time, which is j omega, right? So then we replace here a e raised by j omega t plus alpha by z. This is my equation 4. This gives me the complex velocity. Also, we find the complex acceleration, then I have to find the second order derivative of z with time t. So it becomes simply j omega square times, let me write it neatly, j omega square times a e raised power j omega t plus alpha, j omega square a e raised power j omega t plus alpha. Now j square is minus 1, so it becomes minus omega square z, because a e raised power j omega t plus alpha is z, so it becomes j omega whole square. J square is minus 1, then I have omega square, this thing is z. This is my complex acceleration. Let me name it. This is my complex acceleration. Now remember, we can represent the complex number by a vector. So we can represent z, this dz by dt and second order derivative of z with time by vectors. So let us do that. Let me draw the figure. This is my x-axis. Its length is a. This is omega t plus alpha. Let me part A. Then this is x. This is omega t plus alpha plus pi by 2. This length of this vector is omega a. Let me write it neatly. Its length is omega a. Let this be part B. Then this is x-axis. This will be approximately this way. This length is omega square a. Let me complete it. I will justify it. It is omega t plus alpha plus pi. Let me name it figure 2. Yes, this is my figure 2. Let me use another color now. See, this vector represents z. This vector represents dz by dt, and this vector in part C of figure 2 represents second order derivative of z with time, that is d2z by dt2, right? Now understand it. Let us move to this complex position z. The vector representing it will have length a, and it will make angle omega t plus alpha with the x-axis. So we have shown that length a, and it makes angle omega t plus alpha with the x-axis. Let us move to dz by dt. See, dz by dt has length a omega, and it makes what angle I will tell you. First, let us move to the length. It has length a omega, right? Now, it makes angle omega t plus alpha plus pi by 2 with the x-axis. See why. Remember, in the last lecture, we said if we have some vector representing some complex number, if we multiply that complex number with j, now the new vector will be rotated by pi by 2 radians in counterclockwise sense with respect to the previous vector. See, it is z. dz by dt is j times z. Now this omega appears here. It has length a omega, but this multiplication of j rotates dz by dt compared to z by 90 degree or pi by 2 radians in the counterclockwise sense. So angle made by it will be omega t plus alpha plus pi by 2. Now what about the complex acceleration? d2z by dt2 has length of a omega square, right? A omega square. So it has length a omega square, right? And see then what happens is j square is multiplied to this z. J square is multiplied to z, that's minus 1 is multiplied to it. Is one and the same thing. That means j is multiplied twice to z. So one J will rotate it by 90 degree with respect to Z in counterclockwise sense. Another J will rotate it by further 90 degree or pi by 2 radians. That's why in this figure, the vector representing complex acceleration is rotated with respect to complex position by pi radians. That is 180 degrees, 2 pi by 2 rotations in counterclockwise sense, right? Now see how easily we see the relationship between first how easily we get the derivatives. We have Z, so we easily find the derivative dz by dt. We easily find the acceleration. Now, what is our, as we said, this complex velocity, complex position, and complex acceleration contains mathematically two oscillations. The oscillation along x and oscillation along y. Mathematically, we go forward with these two oscillations, but at the end, we discard the oscillation along y-axis. How we do that? We take the x projection of these vectors representing these complex quantities. See, this projection is my real position. This projection on x-axis is my real velocity. This projection on x-axis of this complex acceleration is my real acceleration d2 x by dt2, this projection, right? So we move forward using complex position, velocity, and acceleration. Then at the end, we take their x components only, that is their projections along x-axis, that give us the real position, velocity, and real acceleration, right? So in a way, we at the end throw away this position along y, velocity along y, and acceleration along y. So we separate the additional oscillation which we are taking along mathematically, but why we take it along? Because it gives us this exponential. It allows us to use this Euler's relation here, right? What we do, let me summarize. We have to analyze oscillation, but we exploit the property of a relationship between uniform circular motion and the simple harmonic motions. Now, to use this Euler's relation, to use complex exponential, we take both of the oscillations, but in actuality, we're discussing single oscillation. Then at the end, we throw the imaginary part of our z, dz by dt and d2z by dt. That means we are throwing away or discarding the oscillation along y at the end, but along the calculation, we consider as if there are two oscillations taking place. This is how this complex exponential usage allows us to move forward in the analysis of vibrations thanks to this Euler's relation. So this is all for today. Try to understand it. Don't waste your time and Don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.